What's the shading color? What kind of shading color is on it? Depends. I think towards the beginning of the season, I was playing center mid, but then I got moved to
Yeah, I don't know why that. I don't know anything myself.
It's not the front people, but it's the middle, or the middle farthest to the side.
All right. So transformations.
Sorry.
Okay, so it says an important aspect of understanding functions is the concept of transformations. Throughout this course, as well as in past and future courses, we will study a variety of functions and their graphs. All of these functions can be viewed through the perspective of transformations. Transformations will weave throughout everything we learn in AP Pre-Calculus, so they never go away, which is why we start with them. So we want a good foundation of them, and then we're just going to see them throughout everything that we do. And they provide a way for us to connect the topics we learn throughout this course. So below is a table of transformations along with how each transformation affects the graph, which a lot of these we've already talked about, except for the one, which would be our horizontal dilation. So we already know that a vertical translation, come on, there we go, is going to move the graph up or down based upon whether or not it's adding or subtracting to the outer function, the outside of the function. We know horizontal translations moves left that are happening on the inside, and that's going to move it left and right. But we also know that it's going to occur opposite of what we see. So if we see that it's added, it's actually going to move it to the left versus to the right. So all these things are as they should be. Then one that we also talked about is a vertical dilation. And so a vertical dilation is some sort of factor that is multiplied to the outer part of the function. And it's going to kind of stretch or compress it. And then there's also a little note down here that if your dilation is a negative value, then it's going to perform that x-axis reflection. So they kind of make that a 2-for-1 special of it reflects and it can stretch. All right, so horizontal dilation is the only one that we haven't talked about. Now, we have talked about the fact that if it's negative, then it will reflect it over the y-axis. So we've touched on that one. I don't know that you touched on that one much last year, but we definitely have talked about it quite a bit this year. Okay, so horizontal dilation. Notice when you're multiplying a number inside of your function, on the inner part of your function, so to the x, what is happening with your factor? What happens? Yeah. Okay, so the thing that you need to think about here is the same thing that you think about when you're talking about a horizontal translation. It's opposite. Yes. Okay, so if I'm multiplying something by a factor of 2, what is opposite multiplication by a factor of 2? Dividing by 2, or the same thing would be like a 1/2, multiplying by a 1/2. And so when it's on the inside, whether it's a translation or a dilation, remember it's going to actually behave opposite of what we think it should. So if it was added, it's going to go left. If it's multiplied, it's not actually going to double the x values. It's going to half it or to third or whatever. And so anything on the inside is opposite. Anything on the outside behaves the way it should. So if we can remember that, then we'll be okay. But the reason I decided to teach this transformation just separate on its own is just for the simple fact that it is so backwards. And it's new. So it goes ahead and it kind of goes through the same thing that I just said. So it says any transformations that affect the x values will occur on the inside of the parentheses. We know that. Those transformations will do the opposite of what it looks like it should do. We know that. And then it talks about the y values, and the y values obviously occur on the outer part of the parentheses or the function itself. And then it says they will do exactly what you think it should do. So behave right. Okay, so on example 1 here on the first page, it says that G is our function and that has been transformed, and F is our original. So I need you to make sure that you understand which one is the original and which one is the transformed function, because the names will matter. So it says let G be a function that is a transformation of the function F. So notice that F is the one that has all the things that are occurring to it, and that gives us G. Does that make sense? So naming functions in AP Pre-Calculus is very important, and making sure you identify, well, where's my start and where's my finish? So it says describe the transformations of the function that will result. And so we've been doing this. This one's not any different than normal. So what's the first transformation we have? Okay, so we've got a vertical dilation by a factor of 2. And since we're going to start seeing more of our horizontal dilations here in a second, we need to make sure that we are identifying whether it's happening vertically or horizontally. So remember, outside is the Y, which makes it vertical. Inside is the X, which makes it horizontal. Then can we all agree that this is going to go right 3? And then up 1. All good? Nothing new? Turn the page. Okay, so the formatting on this lesson isn't the best. So this graph right here actually goes with example 3. So don't assume that that graph goes with example 2, even though I know a lot of times the graph that you're talking about goes under the question. Okay, so example 2 says let n be a function that is a transformation of the function m. What's the original function? And n is what occurs after some stuff happens. And then it tells us the thing. It says describe the transformations of the function m as a result of the function n. So what's the first thing that occurs? Not the y-axis. Yep. So we have an x-axis reflection. Next. Yes. Vertical dilation by a factor of 4. All right, now here's the new one. What's happening here? Yes. Boom. Nice. So just don't forget it flips, just like it does with a left-right shift. That also flips. All right, the next one. We are using this graph here. So it says the graph of y equals f of x consists of 2 line segments and a semicircle. So we can see that there. And it shows its domain. So it says it goes from -3 to 5. And then it says sketch a graph of G on the same axis, but with the given transformation. So what's the easiest way for me to do this? Based on the transformation, what do you think the easiest way to do this example is? Well, yeah, I mean, and what's happening? Yeah, it's going to go left 3 down 4. I think the easiest way to do this is to simply count, right? There's nothing crazy happening here. So left 3, down 4. So take your nice pretty points is what I would do. And then I would plot them and sketch my graph. Now, if there were crazy transformations, I would definitely think about doing this a different way to make sure I did it right. Oh, that's supposed to be a semicircle. Boop, 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 boop. See if I can draw a nice semicircle. Oh, it started off decent. And then he just came up short. All right, so that's what you should have. Easy. You could also write a function rule and then take the order pairs and transform the order pairs and plot those and then connect your lines if you wanted to. I'd say this one's easier. All right, now, example 4. Where we're looking at the graph of h. It says the graph of y equals h of x has a hole at x equals 4. So we've got open circle there. But then notice there's a closed circle down here. So it is an included value in the domain, but that's easy to overlook. And it consists of 3 linear segments. Sketch a graph of k on the same axis where k of x equals that. All right, so this one's a little bit more complicated, so I might want to write a function rule for this one. So let's do that. What's happening to the x values? So we have a horizontal dilation, which means they're going to be multiplied by half. Is there anything else happening to the x? No, because there's nothing else occurring inside the parentheses. Okay, so everything else is going to occur to the y. What's happening to the y?
It's reflected on the x-axis. So it's like
Negative y and then of 1. Yeah. So that's what occurs on the outside of the function. Outside of the parentheses. Okay, so now I would just pick the pretty values and transform them. So like this first one right here is negative 4, negative 3. So when I transform it, half of negative 4 is negative 2. And then that's 4. That goes up there. Okay, then I've got this point here. That's negative 2, 1. So that'll be negative 1, 0. There. So connect. Whoop. Then I have this point, which is 0, negative 2. So that's going to be 0, 3. Yeah. So right there. Let's see. I guess the hole is the next one. The hole is at 4, 2. And that would be 2, negative 1. 2, negative 1, hole. And then I've got the solid point that's like disconnected at 4, -1. So 2, 2. Right there. So here, connect the hole. And then the last point will be 6, 4. So that's 3, -3. Down there. So there's my graph. I hope yours is a little prettier. Mine's not very pretty. So do you see the dilation? How it compressed it in, squeezed it in. Do you think you could do it without a function rule? It'd make me nervous if you tried. I'd write a function rule. It'd make me nervous if I tried to do it without a function rule. All right, turn the page. 5. Okay, so 5, what they do is they give me the domain and the range. And this says it's the same graph as example 3. But in all honesty, you don't need to see the graph to do this question. So they tell me the domain is from -3 to 5. And then my range is from 1 to 3. And it wants to find the new domain and range for the transform function. So we had f, and they did some transformations to f. Okay, so anytime they want you to do this, could you just go back to example 3 and like look at the graph and do it? Yeah, you could. But it's actually just as easy just to apply the function rule to the domain and range as appropriate. So what's happening to the x's on the transform function on G? What's the x transformation? Left 3, right? And so if I was just to make a function rule, we know it'd be x minus 3. Make it go left 3. Okay, and then the y is what's happening. And then down 4. Okay, so if I want the new domain, all I do, since domain is the x values, all I do is apply this function rule to those values right here in the original domain. So the new domain just is going to transform the same way all the points transform. So what's the new domain? And 2. And then the range, I just do what's happening to the y's. So if the y's start at 1, well, after they're transformed, they're going to be at -2. 1 times 2 minus 4. And then it goes to 2. And it's that easy. So we have transform functions and identify their domain and range, but what we haven't done is just taken the domain and range and use that transformation to get the new one. It's just as easy. Okay, here's where things get a little weird. And this is why at the very beginning of the lesson, I told you I need you to really pay attention to which is which and what's happening. Okay, so it said we got a table of values here. So we got the x values, and then we've got the y values for p of x. So it says the table above gives the values for a function p at selected values of x. And then it says let h of x equal 3 times p 2x minus 1. What is the original function? P. What is the transform function? H. Okay, so this is the original. And then what we get out when we do the thing to the original, that's the transformation. That's the transform function. So it says find the following values. So it wants me to find h of -1. So what's it saying? Yes. Okay. So here's the deal. If I'm just taking this right here and I'm replacing that with a -1, I'm just replacing this with a -1. Does that require a flip here? No. Okay. So when do we flip and when do we not flip? What is the difference in this question and then what we were describing in this question? Yes. And what we're doing here is we're taking the transfer, plucking the transformation out, right? So we've got the function that is being described, and we're taking that description and we're plucking it out to apply it to the values to get the new function. Yes? Well, this is not telling me to do that. This is telling me to take an x value and just plug it in. Okay? It's not telling you to extract the type of transformation from the function. You're not going to see this a whole lot, but you got to make sure you know the difference. Okay, so and another indicator is it's not telling me to transform anything. It's just telling me figure out what -1 is. Find the y value at -1 for the transform function. Okay, so this is how we're going to do this. We're going to take this and we're going to plug it in. So we're going to say h of -1 is 3p 2 times -1 and then -1. Okay, so 2 times -1 is -2. Okay, so 3p -2. Now, what is p of -2? Yeah, how do you know? That's why we have the table, because if we're just looking for this value right here, what is that value saying? It's when x is -2, the y value is, so when x is -2, the y value is 1. So I can replace p of -2 with a 1. Do you see how we're working inside out and we're not working kind of outside in? That's the difference in this question and the other ones that we've done. So 3 times 1 minus 1 equals 2. So my answer here is 2. All right, let's do B. B is kind of the same. So I'm just plugging 2 in. So 3p 2 times 2 minus 1. 2 times 2 would be 4. So 3p of 4 minus 1. What is p of 4? 3. So that's what I'm going to replace that with. 3 times 3 minus 1. So that's 8. Okay, 0. So that's going to be 3p of 0 minus 1. What's p of 0? -1. -4. So if we extract the transformation out to create the function rule or to describe the transformation, that's when we flip. If we're just plugging in values into functions, we're not changing anything. We're doing what it tells us to do. 7. So number 7 says the function g is constructed by applying 3 transformations to the graph of f, which is the original. F. A horizontal dilation by a factor of 3, a vertical dilation by a factor of 4, and a vertical dilation by -7 units. So it says if g of x equals, and it gives us the function with variables in there. Find the values of a, b, and c. Okay. So what is a representing? The vertical dilation, which is, yeah. So a would be 4. Okay. Then what does b represent? The horizontal dilation. Okay. So now if I'm taking that and I'm putting it in there, I flip it. What's 1/3? Because think about it. Earlier we had, I don't know what the letter was, but I'll just say it was G of 2x. And we said that was a horizontal dilation by a factor of 1/2. So if I have a factor of 3, then that means that the value on the inside has to be 1/3. Because if I pull that out, it's got to match that. All right, then vertical translation, -7 units. So C has to be -7. For AP Pre-Cal, you do not have to necessarily list out A, B, and C. You don't have to say A equals B equals C equals. If you'll just write it in the form right here, they accept that. So that's fine for your answer. All right. Let's see. This is 8. So 8's talking about the table. It says the table above gives values for a function h at selected x values. Let k of x equal that situation. So what's the original? What? What's the original? H. So this represents the original. It says where A, B, and C are positive constants. In the xy plane, the graph of k is constructed by applying the transformations to the graph of h. So again, that statement right there lets you know that h is the original. It says in this order, we have a horizontal dilation by a factor of 1/2, a vertical dilation by a factor of 3, and a vertical translation by a unit of 1. And it says find the value of k equals -6. So before we do that, let's create our function k of x. So if we're talking about k of x, what is a? Yes. And then what is b? B is 2. And what is c? +1. Okay. So there's our k of x with its transformations applied. So now when I go to find k of -6, do I flip the 2? No. Why? You're just plugging it in, right? So this is like example 5, or not 5, 6 that we did with the table a second ago, except we constructed the transform function, and now we're doing the same thing we did. We're just taking that -6 and figuring out what it is. So 2 times -6 plus 1. So 2 times -6 is -12 plus 1. And what is h of -12? 1. So that would be 4. Just it. Yep. Last one. So the function p is given by this linear equation. So 3x minus 2. It says a graph of r is the image of the graph of p after a horizontal translation of 4 to the graph of p. Is that all? Yeah, that's all, isn't it? Yeah. Okay. I thought there was more to this question, and there's not. It says if r of x equals ax plus b, find the values of a and b. Okay, so if it's a horizontal transformation, where is it going? It's what? To the left or right? And then what value gets affected? The x. Okay. So this is how you would do this. So I've got the equation of the function right here, and I want to transform it to the, what was it? Right 4? Yeah, because it was a positive 4 here. I want to transfer it to the right 4. So I know if I do a horizontal, when I write that transformation, what does it actually look like? No, if I'm going right 4, I'm subtracting 4. So this would be like, I would say, I'm going to take p, and then it's going to be x minus 4, right? That's what it looks like in the transformation. Okay, so if I apply this to the equation, it's going to look like this. It's going to look like 3 minus 2. And that's going to represent r of x. Now, is this in the form that they asked me to put it in? No. What does it want me to do here? Yeah, it wants me to simplify it, distribute it. So when I distribute that, I'm going to have 3x minus 14 for r of x. And so what we would see is this linear graph, if we graphed it, and then we graph this linear graph, it would be transformed to the right 4 units. Any questions? It's just a lot of different things, I feel like. All right, you have an assignment.